So with this one, we've got parallel plate capacitors, which have an initial separation D and an area A. So we know the capacitance is given by A epsilon naught on D. And then we move the capacitors. So let's move them to some final separation DF. And we're told that we want to quadruple different quantities. So first of all, the capacitance. So we want the final capacitance to be equal to 4 times the initial capacitance. So the final capacitance will be given by A epsilon naught on D final, and that will be equal to 4 times the initial capacitance, which was A epsilon naught on D. So you can see the surface area of the plates cancels, epsilon naught cancels, and we can rearrange this to get, well, the final plate separation is equal to the initial plate separation divided by 4. So that's our answer to that part. Next, we want to quadruple the amount of charge. Now, in the question, it says that these capacitor plates were charged and then the battery was disconnected. If the battery is disconnected, then it means that there's nothing which is supplying any charge. And so if there's nothing that's supplying charge, then we can't change the charge. So the charge can not change while the battery is disconnected. So the answer to this part is no. Next, we want to quadruple the energy. And we know that the energy stored in the capacitor is given by a half Q squared on C, which is equal to a half CV squared, which is equal to a half QV. Now, in this case, it's probably easiest to use the first part of this equation here, because we've just said that the charge doesn't change, and we have an expression for the capacitance. So what we want is that the final energy stored will be equal to 4 times the initial energy stored. And so we can write a half Q squared, and then C I'll replace with A epsilon naught D final. So this is A epsilon naught, and then D final ends up at the top. And then that's 4 times the initial energy, which is a half Q squared over the initial capacitance, which is A epsilon naught D. So many of these factors cancel out. The half cancels, the Q squared cancels, the A epsilon naught cancels, and we end up with our final distance is equal to 4 times our initial distance. And finally, the energy density, which is the energy density stored in the electric field between the plates. And we're told that this is given by the expression UE is equal to the potential energy divided by the volume. So we can say we want U in the electric field final to be equal to 4 times U in the electric field initial. And so this is equal to U final divided by the volume. So that'll be a half Q squared D final over A epsilon naught. Now the volume in here is going to be the area times the distance. In this case, it's the final distance. So this will be A times DF, and that'll be equal to 4 times the initial one, which is a half, and then we've got the energy, which is Q squared D over A epsilon naught divided by the volume, which is AD. So what you can see happens here is that the final plate separation cancels out and the initial plate separation cancels out. So this tells us that the energy density is independent of the plate separation. So it doesn't change as we change the plate separation. So it does not change as we change D, which means that the answer to this one is no. We can't separate these a certain amount to make this true.